Okay, let's unpack this. We've all been there, dreaming of the perfect digital assistant. And I'm not just talking about one that answers trivia questions or sets a timer.
Right, something with real agency.
Exactly. I mean, an AI that can truly understand your digital life, one that can see your screen, navigate your most complex software, or, let's be honest, your most fragmented mobile apps, and just execute a really complex multi-step task all on its own.
And that capability, the fully autonomous graphical user interface, or GUI agent, that's basically the holy grail of applied AI right now.
It's what everyone's chasing.
It is. I mean, recent breakthroughs in multimodal LLMs gave us the essential foundational building blocks, the visual perception to see the screen and the high-level language planning to decide the next step.
But there's a catch.
There's a huge catch. The central challenge remains stubbornly persistent.
Yeah.
How do you train these agents reliably for these complex, real-world, multi-turn tasks? How do you do that without the training process becoming just prohibitively expensive or noisy or, prone to factual errors and hallucinations?
That inefficiency, that data bottleneck, is exactly what we are tackling today. We are diving deep into a new technical framework presented in the Step-GUI report. And this was spearheaded by the G-Lab team.
Right.
And this isn't just about showing off a new model. It feels like a foundational shift in how we generate the data, build the models, and then securely deploy these agents.
It is. And our mission today is to really dissect the three innovative pillars that the G-Lab team introduced to kind of finally deliver practical real-world GUI agents. First, we have to understand where their power comes from.
The data pipeline.
The self-evolving data pipeline. And they've powered it using something called the Calibrated Step Reward System, or CSRS. And this system, it basically solves the core problem of getting cheap, high-quality training data.
Okay, so that's pillar one. Then second, we'll shift gears a bit to deployment and security, looking at GUI-MCP, the Model Context Protocol, which is, from what I understand, a novel, standardized approach for secure and crucially privacy-centric deployment across every device you own. So phone, desktop, everything.
Everything. And finally, because if you can't measure true high-frequency usage, you can't really improve practicality, right?
Of course.
So we'll examine Android Daily, which is a completely new benchmark designed specifically to evaluate agents on authentic daily usage scenarios. This is the true, unforgiving test of usefulness.
And before we dive into the, the deep mechanics of the training system, let's just underline the sheer efficiency of what they achieve.
Yeah, the results are pretty striking.
The Step-GUI models, specifically the 4 billion and 8 billion parameter variants, they're built on the Qwen 3VL foundation, and they're setting new standards. The 8B model is state-of-the-art across key benchmarks. 80.2% on AndroidWorld, 48.5% on the really complex OSWorld desktop tasks, and 62.6% on Screenshot Pro.
And the striking detail there, which speaks directly to the future of deployment, is how compact these models are.
Right.
That 80.2% performance on AndroidWorld, that ties with other leading, often much, much larger models. But the source material is careful to note that the compact 4B model is already capable of consumer-grade local deployment.
Wow.
And that is a huge statement. It's about trading massive parameter counts for data quality, which is really the key theme of this entire deep dive.
So let's start where the journey begins. The necessity of these GUI agents and the challenge of building them. We've seen multimodal LLMs get incredibly good at processing images and text.
For sure.
Which gives them that foundational visual perception, like recognizing a button. But why is translating that recognition into accurate multi-step actions in the real world so fundamentally challenging?
The challenge, it really boils down to reliable training data for complex sequential tasks. I mean, think about the difference between answering a single question and, say, executing a 20-step recipe perfectly. Traditional training methods, they relied on subjective, costly, step-level human annotation.
So you had a person sitting there for every single step.
Yes, for every single step in that 20-step sequence, confirming, yes, the model clicked the right button, and yes, that was the right thing to do next.
That sounds incredibly slow and expensive and just prone to human error, especially if the task involves, niche software the annotator doesn't even know.
Precisely. And when a task spans many steps, human annotators can introduce factual errors, or, and this is a critical failure mode, the model, because it's lacking verifiable ground truth at every single intermediate step, it starts to hallucinate its next action. And you end up with these brittle, expensive policies that only work in the exact scenario they were trained on. They just fail the moment the interface changes even slightly.
So Step-GUI needs to be more than just a dedicated agent. It has to be an LLM that retains broad intelligence while gaining this expert domain knowledge about operating systems and apps.
Exactly. It needs world knowledge and fine motor skills.
Right.
It does. And Step-GUI is framed as a multimodal foundation model. The goal isn't just to build a tool that clicks buttons. The goal is to retain rich world knowledge, which is critical for reasoning about what applications should do while mastering that agentic competence.
And that competence includes what specifically?
Well, it's things like precise visual grounding, fine-grained region understanding, and most importantly, accurate instruction-to-action mapping that actually accounts for the state of the interface.
So how do they bridge that gap? How do you get from a generic visual LLM to a specialist GUI agent? It seems like they have this very structured blueprint they call the progressive training philosophy.
They do.
They don't just throw all the data at it at once.
Right. No, it's a rigorous phased approach, a three-stage paradigm that's designed to build capabilities incrementally and progressively. The strategy is to establish a strong, broad base and then use targeted, error-driven refinement.
Okay, let's look at stage 1, mid-training. I'm seeing a huge volume of samples here, around 11.2 million. What's the specific goal of this massive initial stage?
The goal here is all about foundational breadth and consolidating existing knowledge. It's about making sure the model inherits and internalizes broad world knowledge while acquiring the raw skills it needs for agent work.
So the data mix will reflect that.
It does. You have general multimodal understanding samples, about 1.9 million of them, to ensure language fluency and reasoning. Then you've got knowledge consolidation samples, another 2.0 million, to reinforce world understanding, and a massive chunk of grounding data, 2.7 million, for learning precise localization.
So this is where it learns what a button looks like, what a search bar is, and how to understand English instructions related to those elements.
And then they introduce the agent-specific formats. This is where it starts to learn the language of action.
Okay.
You've got action alignment data for instruction-to-action bootstrapping, and a huge volume of multi-step trajectory data, 4.0 million samples, to expose it to diverse planning patterns across multiple steps.
And crucially, they're not just sticking to one OS.
No, and that's critical. They introduced cross-platform samples, around 420,000 of them, from Android, Ubuntu, Windows, and macOS, ensuring that Foundation isn't restricted to just a single digital environment.
That makes perfect sense. You establish the broad base of knowledge, then you introduce the specific syntax of GUI interaction across different operating systems. But what happens in stage 2? Cold start fine-tuning. The number of samples drops dramatically to around 1.67 million.
Yeah.
Why the sudden focus on efficiency?
This is where the training becomes laser-focused. It's all about correction and closing knowledge gaps. The objective shifts from broad exposure to execution refinement and patching knowledge gaps. And they do it through an error-driven knowledge injection strategy.
Error-driven. So they're actually analyzing why the model failed previously and then feeding it corrections, not just more random data.
That is the key strategic insight. Agent failures often stem not just from poor physical execution like, say, missing a click target by a few pixels, but from missing semantic knowledge.
What do you mean by that?
Well, they might not understand what a specific icon means in a foreign application, or they might fail to anticipate an application's specific behavior.
Can you give us an example of how they turn a failure into a successful training sample?
Sure. Let's say the agent is trying to file an expense report, and it fails because it needs to find the attach receipt button. But in this specific app, the button is a small, unlabeled paperclip icon the agent has never seen before.
So it just gets stuck.
It gets stuck. So they diagnose that execution failure, and they convert that missing knowledge, the UI semantics, the app behavior, into VQA pairs, visual question answering pairs.
So they're literally asking the model a question about what it saw.
Yes. They effectively ask the model, what does this paperclip icon typically represent in this context? And they feed it the answer, attachment.
So if the model failed to navigate a settings menu because it didn't recognize the gear icon, they'd create a VQA pair asking, what does this icon represent, and feed that back. It's teaching the model the meaning of the interface, not just the physical location.
Exactly. And if you look at the data mix in this cold start stage, it really reflects this focus. Knowledge data makes up the largest proportion, 52% of the samples. This targeted injection directly addresses the model's diagnosed weaknesses, which enables robust generalization without relying on just generic world knowledge that might dilute the training signal.
That's a very intelligent way to scale an agent. You don't just keep throwing generic data at it. You use its own failures to generate highly specific, high-value training material. It's a targeted learning strategy.
It is. And this brings us directly to the infrastructure that enables all of this targeted learning, the Calibrated Step Reward System, or CSRS.
Okay.
We really need to spend some time here, because this is the self-evolving engine that creates the data pipeline. This is what's behind that staggering claim of 10 to 100 times cost reduction and over 90% annotation accuracy compared to manual step-by-step labeling.
That kind of cost reduction is monumental. I mean, if you can make high-quality training data that much cheaper, you fundamentally change the economics of building AI.
You do.
So let's detail how this system gets around that noisy step-level annotation problem.
It uses something they call trajectory-level calibration, which is the first crucial advantage. Think of it this way. Assessing every single step in a 50-step task is like having a human teacher grade every single sentence a student writes in a 50-page essay.
It's subjective, exhaustive, and it's going to introduce fatigue and error.
For sure. But the Step-GUI team, they decided to change the grading mechanism. CSRS performs validation, a simple binary success or failure check, only at the trajectory level.
The very end of the task.
The very end. Did the agent successfully book the flight? Did the file get expedited? Did the reservation go through? Yes or no? This establishes a high-confidence quality anchor for the entire sequence.
Because the verification is objective. It's tied to the final verifiable outcome, which is way cheaper and less error-prone than checking 50 intermediate clicks.
Infinitely less.
So once they have that reliable, yes, this trajectory worked label, how do they get the detailed step-by-step supervision without paying a human to write it all out?
That's where they introduce the second advantage, LLM-powered data extraction. They use powerful external LLMs, their thinking models, to observe the successful trajectory and then generate the rich multidimensional training data, all anchored to that reliable success label. This is where the magic happens.
And what are those 7 categories of data? They sound like they provide really rich semantic feedback that replaces that human step-level annotation.
They do. They capture a deep understanding of the task. They include progress tracking, state summary, effect prediction, self-reflection, state verification, intent execution, and action prediction.
It's like generating the internal monologue of a highly competent human user.
It's exactly that. It gives the model a dense, deep understanding of why an action was correct, not just what the action was.
And this is where the superiority of the reasoning really comes into play. You mentioned the specific contrast between what a human annotator writes and what the CSRS generates.
It's the perfect illustration.
Yeah.
A human, paid to annotate might only label the action as click center button. It's purely operational.
Right.
The CSRS, using its LLM-powered data extraction, it generates this detailed reasoning, which is effectively the chain of thought. It'll say something like, the text is already selected. The next step is to apply center alignment formatting. I can see the alignment buttons in the toolbar, and I will click the Align Center button. After clicking it, the heading should move to the center of the document.
Wow. That sequence provides the intent, the state verification, the plan, and the predicted outcome. That is fundamentally richer supervision for the next model iteration. It's teaching the model the intent behind the action.
Exactly, not just the physical location of the click. And this ties into the genius of their selective learning strategy. CSRS is smart about failure.
Okay, how so?
Successful trajectories, they yield all 7 data types, both knowledge and action for positive reinforcement. But failed trajectories only yield knowledge-related data, the first 6 categories.
So the rule is learning knowledge from failures, but not learning erroneous actions.
Exactly. This ensures data purity. You don't want the model actively trained to replicate a bad click or an inefficient pathway, but you do want it to learn the semantic knowledge that caused the failure in the first place. For instance, why option A was a dead end, which is a key piece of information for its world model.
Okay, now let's zoom out a little and look at the grounding insight. In GUI environments, grounding can't just be a surface-level visual match. The source material emphasizes that a model needs to acquire capabilities that are analogous to a lightweight world model for virtual environments.
Right, meaning it can't just match a text label to a bounding box. It needs 3 capabilities beyond basic image recognition. First, it needs functional semantics beyond appearance.
So it has to understand that a gear icon means settings, no matter what it looks like.
Irrespective of its color, operating system, or exact design style. That's vital. A settings icon on Android looks different from one on Windows, but they perform the same function.
Makes sense.
The second is latent world state, maintaining an internal representation of what's visible, what's actionable, and how the interface changes, even when those changes aren't immediately visible in the next screenshot.
And the third?
And third, world knowledge of human-computer interaction conventions, or HCI. Like knowing the back button on Android is often in the bottom left, or where to generally find a save button in a typical document editor.
The source also details an iterative grounding cleaning pipeline. This is designed to handle noisy annotations that slip through the initial system. How does that self-purifying process work?
It's a curriculum-based approach combined with self-correction. They initially train on raw data, but then the trained model itself performs rollouts and assigns a confidence score, a pass rate label, to each sample based on how well it did executing the task.
So the model starts grading its own training data.
Precisely. High pass rate samples, the ones the model feels confident about, are used for the main curriculum training. They start with simple localization tasks, then move to functional and intent alignment tasks. This stabilizes the training really quickly.
And what about the really noisy zero pass rate cases, the ones the model completely failed on? Do they just get thrown out?
No, they're initially excluded from early training to protect the learning signal quality. But they aren't discarded. That would be wasted cost. They are revisited later, and if the execution failed due to poor input quality, they are rewritten with rich, step-by-step knowledge and enriched annotations by the CSRS thinking model. Then they're reintroduced as high-quality supervision.
It's a self-purifying, curriculum-based data cycle that continuously improves the quality of the supervision it receives.
Yes.
This closed-loop design explains why the agent can evolve so rapidly. Let's look at the empirical evidence of this self-evolution and the closed-loop training dynamics they show in their figures. The result they saw in AndroidWorld is almost unbelievable.
The best evidence is that dramatic phase transition they observed in the Step-GUI 8B's performance on AndroidWorld. The model essentially jumped from a modest 44.83% success rate in round 2 of training to a stunning 73.40% in round 3.
And your 30-point leap in a single training round. That is explosive nonlinear growth. Why does the source attribute that sudden surge?
That surge is attributed directly to the generation data flow. The model hit a capability threshold where suddenly it was competent enough that the CSRS could start successfully capturing and verifying these long, high-value, successful, long-horizon trajectories that were previously out of its reach.
So it unlocked a new level of data quality.
Exactly. These self-discovered successes, enriched with detailed chain-of-thought reasoning, catalyzed a massive performance boost. It was like finally learning to ride a bike. All the latent skills suddenly clicked into place.
But the performance on OSWorld, the complex desktop tasks with file systems and multiple dense applications, that looks different. It shows a steady advancement, rising from about 30% to over 46%. Why the difference in the curve shape?
Well, desktop tasks are inherently more complex. They involve far more state changes and world knowledge, so that steady, consistent improvement that highlights the efficacy of the refinement data flow. This flow uses self-correction techniques on existing, challenging data. It's systematically identifying and patching the model's weaknesses in those complex desktop decision boundaries, converting difficult failed trajectories into knowledge data for continuous targeted reinforcement.
So on desktop, it's less about a sudden breakthrough and more of a relentless strategic climb because the problems are just that much harder.
That's a great way to put it. The generation data flow drives explosive gains when long horizon successes are found, and the refinement data flow ensures robust, steady improvement on the hardest, most nuanced tasks. It's a powerful combination.
And all this training is underpinned by a rigorous reinforcement learning strategy they call RLBR, or reinforcement learning with verifiable rewards.
Right, and they combine standard optimization techniques with a very fine-grained hybrid reward structure, which is what actually guides the model's behavior.
A hybrid reward structure implies they reward the model for different aspects of its behavior. What are the two main reward components?
The first component is the dense spatial geometric rewards. This is pure, hard science about pixel-level precision, which is vital for clicks and grounding. They use a function that imposes a steep penalty if the agent misses the precise center of the target element.
So it's not enough to just clip the edge of a big button.
Exactly. And critically, they prioritize geometric centrality over simple overlap. This means the agent is rewarded much more heavily for aiming accurately at the center of the target rather than just achieving maximum overlap on a large bounding box. Hitting the center is generally more robust and human-like in real-world GUIs.
Okay, so that's the objective metric, physical precision. What about the second component?
That's the soft capability rewards. This addresses the abstract qualities where hard rules don't apply. Things like intent consistency, task fluency, and sticking to optimal human-preferred pathways. And they use an LLM as a judge mechanism here.
An LLM as a judge?
Yeah. This module provides a complementary soft signal to align the policy with what a competent human user would consider good interaction.
So objective metrics for spatial accuracy and a subjective LLM judge for behavioral quality. If the agent takes 3 unnecessary steps, the LLM as a judge can penalize it, even if the final outcome was technically successful.
Precisely. And finally, they tackle the notoriously difficult problem of exploration and long-horizon tasks, which often suffer from sparse rewards, using a technique that incorporates exploration with hindsight.
Okay.
When long rollouts fail, they don't just discard them entirely. Instead, they run a second pass where they inject ground truth hints into the prompt, guiding the model through the steps it should have taken.
Converting those failed explorations into guided successful samples. That's brilliant.
It allows the model to experience high reward trajectories that were previously beyond its unguided reach, and that prevents the policy from becoming overly conservative and sustains healthy exploration. It's a very sophisticated system.
Okay, we've established how Step-GUI is trained efficiently using the self-evolving high-quality data. Now let's pivot to deployment, which is a massive hurdle in agent development. We're talking about the GUI-MCP, the Model Context Protocol.
Right, and the deployment problem is fragmentation. You have Android, Windows, macOS, dozens of Linux distributions.
And they all speak a different language.
Exactly. Historically, every device platform requires bespoke engineering and proprietary APIs to allow an LLM to take control. This fragmentation just suppresses innovation and keeps the ecosystem locked down. GUI-MCP aims to be the universal standard, defining how agents and devices communicate and enabling an interoperable ecosystem of agents.
So this is the first Model Context Protocol specifically for GUI automation, designed to let an LLM control potentially all major platforms, Ubuntu, macOS, Windows, Android, and iOS through one single unified protocol.
It is, and its architectural elegance lies in its hierarchical dual-layer design. It recognizes that not every task requires the maximum processing power of a massive cloud model.
Okay, let's break down those 2 layers. What does the low-level MCP handle?
The low-level MCP provides atomic device operations. These are the fine-grained controls that any interface needs. Click, swipe, input text, get screenshot, and basic device management functions. It gives the LLM maximum flexibility for step-by-step, fine-grained planning.
So this is the basic toolkit the agent uses to physically interact with the screen.
That's right. And then you have the high-level MCP. This is more like the strategic delegation layer.
Okay.
The high-level MCP focuses on abstract task execution via a single, simple interface.
Right.
Execute task description. This allows the main cloud-based LLM to delegate an entire contained task like buy a cup of coffee or search for white canvas shoes in the app to a locally deployed GUI specialist model.
Which in this case would be the highly efficient Step-GUI 4B model.
Precisely.
This dual-layer approach has 2 massive advantages, starting with improved execution efficiency.
And efficiency is paramount when you're dealing with cloud-based LLMs. The main LLM, the expensive cloud brain, can decide whether it needs fine-grained step-by-step planning, which is the low-level MCP requiring multiple high-latency API calls, or if it can delegate a simple one-shot contained task using the high-level MCP. By offloading routine operations to the local specialist model, you significantly reduce inference overhead and API calls to the main LLM. You save both money and time.
We can use the cross-platform price comparison example from the source material to illustrate this. It's a great example.
It's the perfect scenario. Right. So imagine you want to compare the price of a specific item, say a protein powder, across 3 different e-commerce apps, JD.com, Taobao, and Pinduoduo.
Okay.
The main cloud-based LLM, which has that world knowledge about these retailers, it decomposes that query into 3 parallel execute task calls.
So the cloud model says, okay, task 1, open JD.com and search for protein powder. Task 2, open Taobao and search. Task 3, open Pinduoduo and search.
Exactly. It delegates that entire execution trace. Then the local agent, running securely on your device, takes over and handles the entire 5-step trace for, say, the JD.com task.
Which is awake the app, click search bar.
Type protein powder, click search button, complete. That entire sequence, which could involve multiple API calls and a lot of latency if you routed it back to the cloud every single step, is handled autonomously by the local parameter-efficient model.
Minimizing latency, maximizing speed, and keeping the cost down, the Cloud LLM only needs to receive the final summary comparison.
And that speed and efficiency is a game changer. But the more compelling advantage, and I think the one that's essential for widespread adoption, is enhanced privacy protection. This addresses the single biggest trust hurdle for AI agents.
For sure. I mean, you are rightly concerned about transmitting screenshots of your highly personal interfaces, your banking apps, your private messages, your medical portals, to some external cloud LLM run by a third party.
And GUI-MCP introduces a high privacy mode that directly addresses this by localizing the sensitive visual data. The core insight is this: raw screenshots and sensitive states stay exclusively on the device. They are processed only by the local GUI model, like Step-GUI 4B, which acts as the visual specialist.
So the external cloud LLM, the one providing the high-level reasoning and world knowledge, it never actually sees the raw image data.
Never the raw image. The cloud LLM only receives semantic state summaries that are necessary for task decomposition and high-level decision-making. So instead of transmitting a screenshot of your bank balance, the local model might transmit the semantic summary. Task: compare mortgage rates. Current state: logged into bank portal. Next action needed. Click the products tab.
It's zero image leakage.
Exactly. That truly is the optimal balance. You get to leverage the massive, powerful, world-aware reasoning of a cloud LLM for strategy, but you guarantee data security and compliance via local execution of all the visually sensitive steps.
It suddenly makes AI assistance palatable for high-stakes, everyday financial or medical tasks.
Right. I mean, if you can orchestrate complex multi-app tasks, filing an insurance claim, reviewing sensitive documents, comparing investment platforms, without ever sending a sensitive screenshot off device, you've built a system that users can actually trust for their entire digital life, not just for setting a timer. This shifts the conversation from capability to reliability and trust.
Okay, moving on to evaluation, which brings us to the Android Daily benchmark. The motivation here, as you mentioned, is pretty clear. Existing benchmarks, like the earlier AndroidWorld, they primarily focused on utility apps or abstract tasks. They didn't capture the real friction of daily digital life.
Exactly. The old benchmarks were fine for measuring basic visual grounding, but the reality of daily usage is, high frequency, long horizon, often ambiguous scenarios. Ordering food from a specific vendor, hailing a ride, using loyalty points, or finding a very specific setting deep inside a social media app.
And those are the tasks where an agent provides the most immediate practical value.
The most economic value, and they're also the most prone to failure in the real world. So Android Daily closes that gap. It grounds its task selection not in abstract lab scenarios, but in empirical analysis of actual mobile usage patterns.
It prioritizes the ubiquitous daily scenarios that involve real-world consequences, like spending money or booking time and multi-step decision-making.
For sure. And looking at the scenario focus, the distribution is fascinating because it heavily reflects the areas of highest practical friction and cost. Transportation and shopping just dominate the distribution.
I see transportation accounts for a third of the tasks, 33.19%, and shopping is right behind it at almost 26%.
And these are real-time, dynamic tasks. Then you have social media, entertainment, and local services. These are tasks like finding the cheapest delivery option during a peak hour, comparing two similar products on different retailer sites, or managing your calendar.
Complex, real-time choices that require navigating constantly changing interfaces and dealing with real-world constraints. They are functionally different from simply opening a calculator and adding two numbers.
They are. And the benchmark uses a two-tiered evaluation strategy. Let's start with the static benchmark, which involves analyzing over 3,100 actions.
Okay.
The static evaluation measures single-step prediction accuracy across 8 core action types: awake, click, complete, info, long press, slide, type, and wait. This provides rapid iteration capability during model development. A quick check on the agent's basic motor skills.
And a crucial detail here that boosts realism. It supports multi-solution ground truth annotations.
This is a major improvement. A real mobile interface often provides multiple valid pathways to achieve the same goal. Maybe you can scroll down to find the checkout button, or maybe you can click the floating cart icon in the corner.
Right.
If there are 2 buttons that achieve the next logical step, the agent is correctly credited for choosing either. This prevents models from being penalized for being creative or flexible, which is essential for real-world robustness.
And then you have the end-to-end benchmark 235 tasks evaluating autonomous task completion in fully functional environments, using an LLM-based system to judge whether the final outcome was achieved.
And this is the definitive test of agentic competence. These tasks are characterized by complexity, ambiguity, and different cognitive operation types like filtering, querying, and comparative analysis. If the agent can pass this, it can handle your daily life.
Now let's look at the performance analysis on Android Daily. The static results are startling. They confirm the sheer need for specialized domain training.
The dominance is undeniable. Step-GUI 8B achieves nearly 90% static mastery. Now, compare that to state-of-the-art general models. GPT-4o trails far behind at 17.73%.
Wow, that's a massive gap.
It's a huge performance gap. It confirms that models like Step-GUI possess superior domain-specific knowledge for mobile operations, particularly in navigating and understanding the region-specific applications this benchmark uses.
Yeah.
They just know the language of the mobile UI.
And drilling into specific actions, Step-GUI 8B excels on seemingly complex but vital operations like wait, 95.29% accuracy, and slide, 71.43%.
Yeah, and mastering wait means the agent knows when to pause and wait for the screen to fully load before attempting the next action. That's a temporal planning skill. And mastering side-eye demonstrates fine control over spatial gestures. These are not simple clicks. They are nuanced interactions that demonstrate a deeper understanding of the app's internal process flow.
But the end-to-end benchmark tells a more nuanced story, especially when we look at task complexity.
Yes, this reveals the current frontier. All models still struggle significantly with composite tasks, those requiring multi-step planning and integration, like comparing prices across multiple vendors and then selecting the best one. Success rates there are hovering between 14% and 20%.
Much lower than on the atomic tasks.
Much lower. They do much better on atomic tasks where they're getting 54-61% success. Those are simpler, contained sequences.
This shows that while the single-step execution, the static benchmark, is largely solved by specialized training, the long-horizon complex planning required for integrated real-world tasks is still the frontier the entire industry is pushing toward.
However, what's truly fascinating here is the ambiguity insight. Step-GUI 8B shows unexpected strength in handling high-ambiguity cases, achieving 61.54% success, surpassing a major competitor model at 57.89%.
Why is an agent's ability to handle ambiguity so critical for you, the listener?
Because real-world instructions are rarely perfectly specified or clean. You don't say, click the button with label search located at coordinates x.500, y.100.
No, you say, find the cheapest delivery, or check the first item in my cart.
Exactly. These underspecified instructions require the agent to use world knowledge, make reasonable assumptions, and handle multiple potential solution paths simultaneously. And Step-GUI's grounding loop and its error-driven knowledge injection seem to have fundamentally enhanced its robustness in interpreting that ambiguity.
It's learning to read between the lines.
That's it, which is essential for daily use. It's the difference between a robot that needs explicit programming and an assistant that anticipates your vague request.
Okay, let's synthesize these results and look at the broader implications beyond just the benchmark numbers. First, we have to recognize the overwhelming dominance in end-to-end tasks on established benchmarks.
Absolutely. Reviewing the pass at 3 metrics, which is the most reliable metric as it mitigates non-model related infrastructure failures, Step-GUI 8B sets a new standard. On AndroidWorld, that 80.2% SOTA confirms its mastery in high-friction mobile environments.
But the victory on desktop environments is arguably even more compelling.
I agree, because desktop tasks are historically the hardest domain for agents. On OSWorld verified, Step-GUI 8B hits 48.5%. That significantly outpaces powerful proprietary models from major tech companies, which scored around 23%.
That's a 25.5-point margin on complex desktop reasoning. That demonstrates superior reasoning and interaction in environments like file systems, integrated application suites, and dealing with layered windows.
Areas where agents often just fall apart because the state space is too vast.
And all this performance is achieved with significant parameter efficiency. This is the strategic trade-off we mentioned at the start.
It's the framework, not the size. The Step-GUI 4B and 8B models consistently outperform substantially larger models. The source compares them favorably to models with 30 billion and even 72 billion parameters on almost every metric. The CSRS framework transforms raw compute resources and huge model size into data quality, which then translates directly into intelligence without requiring an unmanageable parameter budget.
And that's the key to local deployment.
That is the key.
Which brings us to the crucial test for any specialized AI. Did all this specialized GUI training harm the agent's general intelligence? Did they trade broad knowledge for narrow expertise?
And that is the ultimate litmus test for any specialist foundation model. And the answer, surprisingly, is a resounding no. Step-GUI 8b was rigorously evaluated on mainstream multimodal benchmarks, and it maintains, or in some cases, improves performance over its base model.
Can you give us those specific numbers again?
For instance, it scores 89.0 on the V multimodal benchmark, slightly surpassing the base Qwen3 VL8B Instruct model, and it hits 74.4 on Mathvista Mini. This proves the training successfully enhanced GUI-specific capabilities while preserving and even boosting broad multimodal understanding.
So it's a true specialist and a generalist. And why is maintaining general intelligence so vital for a GI agent?
Because a real-world task is never purely about clicking. Booking a flight involves reasoning about geography, prices, dates, currency conversion, comparing abstract concepts, all tasks that require general intelligence.
Right.
If training only optimized for clicking, the agent would fail the moment it needed to read a receipt in a complex format or perform a quick calculation. This non-compromise on general skills means it is reliable for practical deployment.
So if we look at the full picture, the self-evolving data, the efficient models, the secure protocol, and the real-world benchmarking, what does this holistic framework ultimately represent for the future of digital assistance?
It represents a complete, deployable blueprint. The CSRS solves the high-quality data generation problem, the efficient Step-GUI models provide the specialized intelligence, the GUI-MCP standardizes secure deployment, and Android Daily validates against authentic usage. It bridges that critical historical gap between promising research capabilities and reliable daily AI assistance that the general consumer can actually use.
That was a tremendous deep dive into the engineering required to build the next generation of truly competent, invisible digital assistants. Let's quickly recap the innovative, self-improving cycle put forth by the GUI team.
It's an iterative three-part loop. The Calibrated Step Reward System, CSRS, generates high-confidence, verified data by anchoring dense LLM-generated reasoning to reliable trajectory-level success labels.
Okay.
This data then trains the highly parameter-efficient Step-GUI models. These models are then securely deployed across diverse operating systems using the GUI-MCP, which is a standardized protocol that preserves user privacy through essential local execution.
And finally, the entire system is rigorously validated against real high-frequency user tasks, not just synthetic lab puzzles, using the Android Daily benchmark, ensuring practicality.
This approach is robust, scalable, and highly efficient. But here's the final provocative thought for you to mull over.
Okay.
The ability of the compact Step-GUI 4B model to achieve competitive SOTA results while being deployed locally, combined with the GUI-MCP's high privacy mode, suggests a really radical shift in how we interact with technology.
If complex GUI tasks, filing reports, comparing cross-platform prices, managing settings, paying bills, can all be orchestrated and executed without ever sending sensitive screenshots off device, what are the broader implications for the future of operating systems and application design itself?
Will the local GUI agent soon become the only interface layer we truly need to manage our increasingly fragmented digital lives?
Yeah.
If the AI can navigate the apps better and faster than we can, the complexity of the applications themselves may just fade into the background, managed entirely by an invisible, personalized assistant running securely right on your device.
That's a fascinating thought.
It makes you wonder how long traditional graphical interfaces will remain the primary method of interaction if this technology accelerates, reducing all interaction down to a simple verbal request to the local agent.
It certainly makes you think about who is truly driving the car when we open an application. That's a powerful thought to end on. Thank you for guiding us through this fascinating report.
My pleasure.
And thank you for joining us for the deep dive. We'll catch you next time.